We saw that the solar system began with pre-solar grains, with a nebula filled with gas and dust, with pre-solar grains containing 12 minerals, the minerals. These pre-solar grains were the ejecta of stars, either red giants or supernovae, and if you're unfamiliar with the world of pre-solar grains, you can check out this tag. It's a really short video that will tell you what we're dealing with. These pre-solar grains went through their first reworking from those 12 minerals. This happened when the sun entered its T-Tauri phase and sent radiation outwards, melting many pre-solar grains around it, and these now sticky grains collided with one another, making bigger droplets which froze out as it cooled off, and they were sometimes remelted through further pulses from the sun and perhaps radiation from more local sources. And these frozen droplets clung together with loose matter and other frozen droplets, and they continued to grow more and more, but not yet reaching the level of collisions and radiation that would rework the minerals beyond the stage of these droplets, or chondrules. These chondrules, along with the bits of matter that form the cement of the meteorites that contain them, comes to us in the form of chondrite meteorites. Chondrite meteorites are far and away the most dominant form of meteorite type that falls to Earth. And they point us to this early period in the solar system's history, and we can thus peer into these meteorites to find out about the early evolution of the planets in this pre-planetary phase. One nice way of following this thread is that of mineral evolution. There are over 4,700 mineral types that have been identified on Earth, but as we saw in the video showing up in the tag, after the death of the first stars, there were 12 mineral types around. And the same is the case for the cloud that makes up the solar system, but with this melting and then coming together and freezing of matter, many new minerals were formed, and the amount of minerals jumped from 12 to 60. The chondrites are not all alike, but they overwhelmingly fall into three main types. The first type is the so-called ordinary chondrite. Ordinary chondrites are these stony meteorites with these chondrules stuck in them. And they're differentiated by level of iron content, with H chondrites being higher levels of iron, L chondrites being less, and LL chondrites even less still. They make up 87% of all meteorites that fall to Earth, and you can clearly see the droplets in them. Carbonaceous chondrites are a different breed. They make up nearly 5% of all meteorites. They're relatively high in carbon, and they have lots of water, up to 22%. That means that they never went through any serious burning phase where the water would have melted off. Their chondrules are smaller, if they're there at all, having been weathered away. And the water that was there weathering these rocks had another effect of creating the first clay minerals within these chondrites. Also, very importantly, these carbonaceous chondrites have lots of organic molecules. Lastly, for our discussion anyway, there are the Enstatite chondrites. Less than 2% of the rocks that are falling from the heavens. These are oxygen poor, so they create some minerals that are very uncommon on Earth. Because there's so little oxygen, many elements that would normally bond to oxygen can't, so they bond to sulfur. This speaks of an oxygen-depleted atmosphere in the early solar system. These are the chondrites, within which are the chondrules, which come from the time when our sun sent out its first radiation. Next up will be the achondrites, the rest of the meteorites, those that come from the processes that follow this chondritic phase.